And live. Excellent, excellent, excellent. Fun stuff. Okay. In the beginning of the year, we obviously fell a bit behind because of circumstances that we were faced with. I only saw you guys once a week for the most part. Class was split in half. We weren't able to do as much as I wanted to do with that material. In the past, I would spend a bit more time with you guys actually going out and collecting data and doing a whole bunch of stuff in groups, but unfortunately, that was cut short. So we were a bit behind, and we're still a tiny bit behind compared to the pace that I want to be on. But in reality, we are only, according to my pace that I set for myself last year, we're only about a week and a half behind where I want to be. So we are in pretty good shape, One thing I do want to mention, while it's fresh in my mind because we had a large discussion about them yesterday during our department meeting, but just so you guys keep it in the back of your mind, midterms. I'm going to mention them on and off for the next several weeks and whatnot, just to give you guys the heads up. But midterms should be the week of January 25th. There was a discrepancy in some of the calendars where I think some of you may have been sent calendars that had the wrong dates on them. But that'd be fun. And yes, there is a midterm for AP Stat. Yes, there's a midterm. Yes, there's a final exam for AP Stat. But the final exam is going to look much different than the midterm because the final exam will take place after the AP test. I don't know. It's going to be a fun year. We'll see. Anyway, what I would like to do today, as I mentioned, we're going to be deep diving a bit more into linear regression. But we are going to be looking at something that has an... Let me flip my screen and show you what I'm referring to. Not those words. But this chart right here. Come on, little chart. Work with me. There we go. This chart just shows population measured in millions of people for some place. Doesn't matter what the place is. But you can see the years there, of course, the year being 1800 all the way up to the year 2000. What I would like to do is I would like you to create the scatter plot. I would like you to run the linear regression with your diagnostics on, of course. And then I would like you to look at the residual plot. Now, just for the sake of argument, you could technically input the years in one of two ways. And both ways would technically be acceptable. You could enter the year 1800 as 0. You could enter in the year 1825 as 25. And then simply put, the scale on the x-axis would just be years since 1800. You could also just enter in the year as it is. You could literally enter in the year 1800, 1825, 1850, and whatnot. It would be to our advantage. I want to be very clear about this. It would be to our advantage if you entered it in the first way that I mentioned, where you enter in 0 for the year 1800, 25 for the year 1825, 50 for the year 1850, etc., and you let your x values be years since 1800. It would be to our benefit if you did that. So it takes a little time right now. Enter in this data into L1 and L2. Look at the scatter plot. Do the linear regression. Make sure your diagnostics are on. But then my ultimate goal is you got to look at that residual plot. Look at that residual plot. Take the next few minutes, knock that out. Just for the sake of argument, and I'm checking myself because I need to make sure that I entered in this data correctly. I'll come back to that screen in a moment. But just for the sake of argument, for those who may have gotten this far, did anybody get the same numbers that I got? Okay, good. Just making sure. I wanted to make sure I didn't make a mistake. I wanted to make sure I did not make a mistake when entering that data. So I'll flip the screen back just so you can see the chart again, but then I'll kind of review what we're doing with this. Shaboo. Oh, it didn't do it. Boom, there it is. There's several things, as you guys are wrapping that up, there's several things I do want to point out in regards to little checks for yourself. Determining whether or not a linear regression is appropriate to perform on such a set of data. I mean, number one, yes, it is quantitative data. You need to make sure you have quantitative data. Number two, we'd have to look at the scatter plot to see if it was straight enough. And then based on the scatter plot, we could determine whether or not there were any visible outliers. So let me actually do that real quick. Again, just for the sake of argument. Oh, you can't see it. Chip down. Just for the sake of argument, there's my data entered into L1 and L2. As I said, I did 0, 25, 50, etc. For years since 1800 and the population of whatever place we're referring to. I turned on my plot 1 to be able to look at the scatter plot. It's automatically set to scatter plot, L1, L2. I zoom 9'd it, and I got this. Now, if you know anything about the concept of population, you would know that population tends not to be linear. Population tends to be a bit more curved. Population tends to be a bit more exponential. Were you guys ever taught the logistic curve? Was anyone ever taught a curve that looks like this? Not a sine curve, something like that. You have. Cool. Like it has an asymptote of top like that. Yeah. Some of you have, some of you haven't. That's okay. It's just the general concept behind, yes, a population will keep growing exponentially, but then ultimately you're going to run out of room with whatever container is containing that population, like a bacteria in a petri dish, and eventually it's just going to reach it's going to reach capacity. That's what people think is going to happen to the Earth. Whatever. Anyway, but that's another point altogether. This clearly looks more curved than anything else. Ooh, I'm a little bit peeved by that. But I mean, I guess, with a couple of points here, I guess you could say, I don't know. Let's run the regression. Let's run the linear regression. Let's just see what happens. Is it straight enough? Sure. Why not? I don't know. Of course, we do have a fourth check to see whether or not a linear regression is appropriate. The fourth check is actually looking at the residual graph. Again, this is stuff that we've done. I'm just kind of recapping it to kind of see where we go with this. So if I were to run this linear regression, get rid of that, there we go, which I've already done, but whatever. And again, my diagnostics are already turned on. I turned my diagnostics on. I could run that regression and it would calculate this information as I showed you before. Man, that R value is very strong. That R value is very close to 1. Absolutely, yes, it is. It's just what that thing. Okay, cool. Slope, y-intercept, all that great stuff. Oh, no. That would have been sad. If I have died, would anyone have laughed? You guys are liars. Anyway, put that back. Now, the residual graph is what's going to determine whether or not, definitively whether or not, a linear regression is appropriate. Let's take a look. Second y equals, I got to change that L2 to be resid. And I do that by hitting second stat, going down to resid. And let's take a look. Zoom 9 it. Oh, clearly there is a pattern. Clearly there is a pattern in the residual graph. That is not good. Oh, well, I guess we call it a day on this problem. We can't run a linear regression. Oh, sad, tears everywhere. Not so fast. There is a way in statistics to what we call re-express our data in such a way in order to make the linear regression appropriate. There are various adjustments that we can do in order to force that, which is what I'm going to be getting into today. There is a way to re-express that data using your lists, rerunning some linear regressions, rechecking the residual graph to make sure that it is scattered, and making an appropriate regression so that we can have some kind of an equation that actually measures the data the way that we need it to. It's going to be nice. Now, it's going to be a little weird because, again, you don't have a ton of room on your desks, and I apologize for that. But you will still need those Chromebooks out to use the calculators because I need you to have the practice with going in and out of lists. But I am going to need, if you do not already have them out, I am going to need those notebooks out and open. Zooming out, zooming out, zooming out, boom. Come on, you. Zoom out. There we go. Ah! Again, I do apologize for the lack of room. Okay. Today is the 9th. And this is called re-expressing data. Now, it's going to be a little slow going if you've never done this very quickly in the calculator, but that's the whole point. I want you to get the practice with this. In the event your residual graph disqualifies the appropriateness of a linear model, which it did in our example, then you can alter the data. Actually, no, alter the look of your data. That makes more sense. In the event that your residual graph disqualifies the appropriateness of a linear model, then you can alter the look of your data. By changing the y values. Now, I will specify that there may be certain instances in which people do change the x values, which is also allowed. I have also seen in very rare instances people altering both the x and the y values, but those are more rare instances. Typically, when people re-express data, they focus on changing just the y values to see what they can do, and they exhaust every possibility. And then if nothing works, then they try other things. But we're going to focus on changing the y values. By changing the y values, you can find the, quote, most appropriate residual plot. Now, this seems very counterintuitive. You're going to change the y values in order to find something that's more appropriate? That doesn't make much. Why would you change the data points? Changing the data points is immoral. Why would you do that? Any good statistician wouldn't do that. Well, we're going to change them just temporarily. We're going to change them temporarily in order to run the appropriate linear model. And the equation that we eventually get is going to reflect what we did. It's going to be nice. It's going to work out. We're all going to high five in the end at a good distance. Well, maybe I will, but whatever. So by changing the y values, we can find the, quote, most appropriate residual plot. Now, in order to get into the details of this, I have to show you something first and then explain it later. I have to show you something first and then explain it later. So what I'm about to show you, you're going to be like, what the heck is this? Don't worry. I just have to have it down as a reference so that when I do explain it, it'll make a little bit more sense, because now you're going to be like, oh, that's what he was referring to. So I got to draw a ladder. And I would like you to draw this ladder as well. There we go. There's my ladder. This is called the ladder of powers. This is called the ladder of powers. The idea is that this is the way in which we potentially will be changing our Y values. This is the way in which we will be potentially changing our Y values. I say potentially because, well, maybe one of them will work. Definitely not all of them, but maybe one of them will work. Maybe one of them will look better than the others. And when I call it a ladder of powers, it's the way in which I'm changing the Y values. I'm changing the Y values by raising it to a certain power. So if I start at the top of the ladder, I would be squaring all of the Y values, rerunning that regression, and seeing if the residual plot was appropriate. And if that didn't work, I'd keep running down the ladder. It seems silly to have this one in here, because what happens when you raise something to the first power? Say again? Just it stays the same. It's the same thing. It doesn't do anything. But that's where we started from. That's the part of the ladder that we're starting with. That's where our Y values are staying exactly the same. And clearly, that residual graph did not look appropriate. What does it mean to raise something to the 1/2 power? Say again? Square rooting it. Yeah. You're actually square rooting the Y values. Now, this is a little strange. This is a little strange. I'm going to talk out of both sides of my mouth right now. What does it mean when you raise something to the 0 power? What typically happens? Yeah, it's just they all become 1, right? You raise anything to the 0 power, you get a 1. We're not going to actually do that. We're going to revisit something that you saw in Algebra 2. Do y'all know what you did in Algebra 2 that you may are dying to forget? You remember logarithms? Evil laugh. Anyway, this sorry. Negative exponent. You guys remember negative exponents where you take the reciprocal? Yeah, same concept, raising it to the negative 1/2 and then raising it to the negative first power. You don't have to always do logarithms. You don't always have to do square roots. It depends. It depends on which residual plot gave you the most appropriate look. We're going to go through them. So let me put some addendums on this ladder of powers real quick. First of all, off to the side over here, I'm going to write, you can alter the Y values by the ladder of powers, which is nice. Now, in terms of the Y values, you can square them. You can do nothing, which clearly is not working, raising it to the first power. As we talked about, you can take this square root by raising it to the 1/2 power. As I mentioned, we're not actually raising it to the 0 power. It would be a logarithm. Typically, we would just stick with a log base 10 and not all that other stuff that y'all did. So fun. You guys didn't like logarithms? Dude, I love the logarithms. It's amazing. Anyway, this is 1 over the square root of y, which you can see it takes the reciprocal and then still takes the square root. And this is that inverse 1 over y. This is the ladder of powers. So, this is what we're going to do. Now, I'm going to do this on my calculator, and I want you to get the practice doing it as well. So I want you to follow along with me and get the same results. I need you to, because eventually you're going to be doing this on your own. And if you're doing it on your own, again, I want you to have the practice. So I'm going to zoom in on my calculator. And we are going to go up technically we're going to start at the top. You can start wherever you want in the ladder of powers. It doesn't really matter where you start, but I'm going to start at the top and work my way down. So first, I'm going to go into my lists. And I'm going to go up to L3. I'm going to highlight L3. You see, I just moved the arrow keys and I just highlighted L3 just like that. Now, since I'm starting at the top of the ladder of powers, the first power is a square. I'm going to type in the following. Look what I just typed in at the bottom of the screen right there. Now, just for the sake of argument, I may not have verbalized this enough, but where did I get that L2 from? There's two places I could technically get that L2 from. That's one way of doing it. There are two ways of doing it, but that's one way of doing it. He said that if you hit second stat, you could find your list of lists and just put in L2. Anyone know the easier way? Do you know the easier way? Second and then the number 2. If you look above the number 2 on your calculator, I believe if you have a regular 83, it should be in yellow, but if you have one of the 84s, it should be in like blue or whatever. Yeah. And then square it. Now, if you did it in the appropriate location that I did it, look what happens when I hit enter. When I hit enter, these numbers pop up. These numbers prop up. Prop up, pop up. Excellent. It populates the list. No pun intended, because this is population. Anyway. So here's what we have to do now. We have to run another linear regression. But this time, we have to tell the calculator, you're not using L1, L2 this time, you're using L1, L3. Now, in my calculator, if I went to linreg, it pops up as this. On most of your calculators, it comes up to that interface screen. Am I correct? Cool. Where they tell you X list, Y list. You got to change your Y list to say L3. Second 3 will give you that L3. I have to tell the calculator this. In my calculator, I have to type it in like that. Because if I type it in that fashion, I'm telling you, hey, no, use the X list in L1, and for your Y list, use L3. And I'm going to rerun this regression. Let's see what happens. Chapow. Boom. I got these numbers. Couple of things I want you to notice as we're going through this. What did it do to my R value? Yeah, it went down a little bit. That's okay. That's okay. We're going to deal with this. We're going to deal with this. We're trying to re-express the data. Yes, the R went down, but that's not the point. We are trying to re-express the data so that we can find a better residual plot. I have to look at my residual plot. Now, I believe if I did this correctly, yes, look at that. It's still set up as resid. And you see, the thing is, when you rerun that linear regression, this residual list automatically repopulates. When you run that regression, that resid list is automatically redone, but it's still called resid. So I don't have to change anything. All I got to do is zoom 9 it. If I zoom 9, chaboom, oh, different residual plot. Question, even though it was a different residual plot, is there still a pattern? Yeah, there's definitely still a pattern. Crap. Clearly, raising it to the second power did not work. So now I have to go down my ladder of powers. I got to go down the ladder of powers. Well, the next number on the ladder of powers is a 1. I'm going to skip that because that's literally what we started with. The next power that I got to go to is 1/2, which is the square root. So here's what I'm going to do. I'm going to go back into stat, edit. I'm going to go up to L3. Now, you could do one of two things here. You could clear it if you wanted to, but you actually don't have to clear it. If you hit clear and enter, it would go away, but you didn't actually have to do that. Well, let me do it again. So that was the square right there, but now I'm going to change it. I'm going to change it to square root. Square root of L2. I got to type in square root of L2. I mean, you could do to the 1/2 power, but I'm just going to do this. It's easier to do it this way. Boom! And it changes all of those values. It changes all of the y values. It re-expresses them as the square root of all of those y values. Phenomenal. So now I got to do the same thing. Now I have to rerun a linear regression. Let me go do that. Rerun a linear regression. But I have to rerun it with L1 and L3. Now, I believe that if you guys go back into the interface, is it automatically still L1, L3? Cool. So most of you don't have to change anything. I do, because I have a dinky calculator. L1, L3. Chapoom. Whoa, look at that R value. Now, again, the R value is not the end-all, be-all. The R value is not the end-all, be-all of this thing, but that is a unbelievably strong R value. What's the strongest you can have? Or? Yeah. But this is still pretty darn strong. You can have 1 or -1, but most likely you're not going to get that with real data. Okay. I did the residual. It repopulated my resid list. Just double checking. Yes, it's still L1 resid. So I don't even have to check that if it's L1 resid. All I got to do is zoom 9 it. Okay. Now one could argue that there's still a slight pattern in this residual, but it's definitely less of a pattern. Now, spoiler, the square root on the ladder is going to be the one that we choose. But at this exact moment, you don't know that, other than me telling you. The way that I make the decision as to which power that I end up using is I keep going down the ladder to kind of compare one against the other. Now, clearly, squaring it did not work. Square rooting it got me something better. It's a little more scattered, but it kind of has a pattern. Let's take a look at the logarithm, because here's what's going to happen. If the logarithm makes more of a pattern than this, that tells me that I got to go back to this. You're basically going up and down the ladder of powers in order to determine, okay, which one gives me the best residual plot? Which one gives me the most scattered residual plot? Clearly, y squared did not work. I went to square root. It gave me this. Okay, cool. Let me try logarithm. Now, just watch with your eyes real quick. I don't want you to do this. I don't want you to change your data right now. I just want you to watch what I'm going to do, because I want you to see how fast this can be done. If I was, okay, I need to change this. I'm going to change it to a logarithm. I'm going to go log of L2. Boom. I'm going to rerun my residual. Boom. I'm going to look at zoom 9. There it is with logarithm. Can we all agree that logarithm sucks? Okay, hold on. Let me rephrase. Not that logarithms suck in general, because logarithms are awesome, but can we agree that the logarithm gave us a residual that has way more of a pattern? Yes. That is the indicator. Because logarithms gave us way more of a pattern, dude, I got to go back to square root. Now, square root may not be ideal. A square root function may not be ideal, but it is better than the linear function that we started with. It's better than the square, and it's better than the logarithm. I mean, I could keep going down to check these, but because logarithm went back to a real pattern, it's most likely, yeah, maybe I should try square root. Okay, let's do that. Now, I had you not change yours. I had you not change yours just because I wanted you to keep that data. Let me write a little note here. So for the example of population, in the example of population, square root of y gave the, quote, most scattered residual graph. In the example for population, the square root of y gave the most scattered residual graph. So here's what we do. Let me change my data back so that you have the same information that I do. Go back to my list. Change L3 to be the square root of L2. Rerun the residual. Boom. Excellent. Okay. I mean, I could check the rest of them, but this one looks pretty good. So you guys got these numbers. Am I correct on your screens? Okay. Several people are like, ah. Okay, just making sure. These are the numbers that you got. Here's what we do. Here's what we're going to write down. Zoom out just a little. Because of the residual plot giving me the best one there, I'm going to write down the following. The square root of y hat is equal to 0.0744x plus 1.4, what do I round to? Yeah, I'll go 6.9. I don't know why. Whatever. But that looks good to me. There's our linear model, quote unquote linear model. It's not actually a linear model anymore, clearly. I mean, I do have that slope and y-intercept, but now those y values had been re-expressed. The y values had been re-expressed as a square root. Whatever you end up doing to the y values, you got to put that function around that y hat. That's what was next to that ladder of powers. Because whatever you end up doing to those y values is what you literally write on the left side of that linear equation. So now, which by the way, just for the sake of argument, x was number of years since 1800, and y was the population. Cool. So now if I want to make a prediction, for the year 2020, for the sake of argument, let's predict population in the year 2020. First of all, what am I plugging in for x? If I'm making a prediction for the year 2020, what am I plugging in for x? 220. Okay. Now watch what's going to happen here. Square root of y hat equals 0.0744 times 220 plus 1.469. I put in 220 because it's number of years since 1800. I'm going to go 0.0744 times 220 plus 1.469. Boom. It gets me the following. That's a hat. There we go. 17.837. But of course, in order to get the y hat by itself, I have to square both sides. I got to square both sides, and I end up with y hat equals 318.16 approximately. And I believe, if I flip back here real quick, yep, it was measured in millions of people. Millions. That's what millions, yeah. And that would be appropriate. That would be appropriate to do. Now, as much as you all may have hated logarithms, let me just ask you a question, because I did not teach you this. Someone else taught you this. But let's just pretend for a moment that instead of square root, let's just pretend it was a logarithm. If I had log of y hat equal to some number like, 18, I'll just change it. I did not teach you this. I want to know what you remember. How does one get y by itself? Algebra 2. Not in this case, no. E is what you would refer to as the natural logarithm. That is log base E. This is not log base E. What is this? Log base what? Log base 10. I got it. It clicked in my head what you were saying. The thing threw me off. Yes. 10 to the 18th power. If it was a logarithm. If it was. Which clearly it's not in this case. But if it was, that's what you would do. So if it was ln, which, by the way, just for the sake of argument, I have seen regressions re-expressed with natural logarithms. And if it was a natural, my marker. If it was a natural logarithm like ln, ln, that's where you would have to use the e. Gold star to who can tell me what mathematician is the reason why it's called E. Oh my goodness, I got two of you. Say it at the same time. Do it. Say it again. It's Euler. It's pronounced Euler. Yes. Leonhard Euler. Around age 30, he went blind in one eye. And then later on, he went blind in both eyes. You know that? He kept doing math. He did it in his head, and he had his son write it down for him. Anyway, great guy. One of the greatest mathematicians of the 1700s. He is the one that was the first one to derive this. He was the first one to derive that, which is amazing to me. But anyway, I digress. What I'd like to do to wrap up today, because we got about 15 minutes, what I'd like to do is I would like to try some multiple choice questions. Now, again, in the past, I would have this whole system of being able to break you up into groups and you'd all compete against each other. And it would be amazing. I can't do that this year. It was one of my favorite things to do, where I would have you like compete tooth and nail against each other. There'd be trash talking and team names. Can't do it. Unfortunately, I can't do it. So what I'm going to ask for the Chromebooks and the notebooks. You don't really need them either. Chromebooks and notebooks, you can close them. Pull out that white erase board underneath your desk. See if you can, if there's a marker still attached to it. If there's not a marker attached to it, then I can throw something at you in a little bit. Yeah. Oh, one second. I'm gonna put this down. Is there one on the back wall? I could have sworn they were like rolling away. I swear, I think the janitor was like throwing them out on me. Anyway, here's one. Oh, here we go. Oh my gosh, there's a lot more. Okay, hold on. Get ready. I'm gonna throw them all at once. Okay? No, I'm not. The what? One of the other desks around you may have it. Catch. Oh. Yep. This is fun because you guys have guards now, so I can throw them like directly at you. I know, and it won't hurt. So, yeah. I don't know what happened there. was a bad throw. All right, cool. So, again, your AP test, did it work? Oh, still need whiteboard. Is there none? Oh, are you kidding me? There's a pile right there. Can you hand her one? I'm sorry. I thought they were underneath all the other desks, but apparently not. So 50% of your AP test is multiple choice questions. 50%. Now, we obviously, when I give you various assessments and I give you the feedback on those assessments, a lot of those assessments are based on free response questions. But I also have to train you up in multiple choice questions. It's just the way that this thing is. And it's a little bit of a pain. So let me just start you off with something like this. Now I'm going to read this. Obviously, you're all behind barriers, blah, 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 blah. I'm going to zoom in on this. I'm going to read this. We're going to see how this one goes. Hold on. Come on, you. Focus. There we go. Suppose the correlation is negative. Given 2 points from the scatter plot, which of the following is possible? I'm going to read through these again. Number one, the first point has a larger x value and a smaller y value than the second point. Or, number two, the first point has a larger x value and a larger y value than the second point. Or number three, the first point has a smaller x value and a larger y value than the second point. Now, when you look at a question like this, I want you to feel anger. Because the people who write these questions, the AP people who write these questions, do you know how they feel about you? They hate you. They want you to fail. They write these questions specifically to mess you up. Take a couple minutes, think about that, write down the letter. Don't hold it up. I'll tell you when to hold it up. Is anyone familiar with the kid show Bluey? No? Okay, whatever. My wife just texted me something. I thought it was funny. I'll tell you about after this question. Now, there's a lot of you, so I'm not actually going to write down the results of what you get. I just kind of want to see a consensus as to what you think the answer is. So make sure the letter is large enough so I can see it. Hold them up. Let me see it. Even if you don't think you know, pick a letter. Even if you don't think you know, pick a letter, because I would like to see the consensus as to what people got. Oh, I can't see it. The thing's in the way. There it is. Yes. All right. I'll probably ask for you guys to hold it above the barrier next time, but okay. All right. There's a nice mix. There was a huge mix of letters in this whole thing. And I saw, actually, you were drawing some of the scatter plots out, which is exactly what I'm about to do. He was drawing some of the scatter plots out. Oh, my goodness. Here we go. Scatter plot. So let's see. The correlation is negative. Cool. Okay, so there's a correlation that's negative. Awesome. Given 2 points from the scatter plot, meaning 2 random points from the scatter plot, which of the following is possible? Okay. The first point has a larger x value and a smaller y value than the second point. The 2 points that I circled fit that criteria. Larger x value, smaller y value. Yes. Okay. Let me look at the second one. The first point has a larger x value and a larger y value. All right. It's true right there. It's absolutely true right there. Larger x value and larger y value. You kind of know where this is going. The first point has a smaller x value and a larger y value than the second. Smaller x, larger y. All 3 of them are true. All three of them are true. Boom. There it is, E. See, the thing is, with a scatter plot, anything like that is possible because the points are scattered. They don't all line up in a straight line. If they all lined up in a straight line, they wouldn't call it a scatter plot. They call it a line. I don't know, whatever. Anyway, so my wife texts me. She says that she and my daughter made a breakfast smoothie, and she was going to add spinach to a breakfast smoothie. If you haven't done that, whatever. And she was going to pick out of a salad mix, but before she could, the 2-year-old grabbed a huge handful of spinach, and threw it into the cup. And when she gave her the cup this morning, and then she blended it all in. And then when my daughter took a sip of it, she said, salad. I'm like, that's amazing. Anyway, back to this. Oh, my goodness gracious. Here we go. Which of the following scatter plots could have resulted in the residual plot? The y-axis scales are not the same in the scatter plots as the residual plot. So which of the following scatter plots could have resulted from that residual plot? Or, yeah, could have resulted in this residual plot. Now, strategies. If you are doing the multiple choice on the AP test, you definitely go through all of the questions and answer exactly what you can. If you're unsure, leave it blank. But I caution you, leave it blank temporarily. Leave the questions alone that you're like, I got to spend more time on this. Answer the questions that you absolutely know you have the answer to, or that you're pretty confident on. Then, if you're running out of time, you need to make your best educated guess. They do not take points away for wrong answers. So if you guess and you get it right, happy day. It can happen. I've had students in the past, years ago, who, there was no chance that student was passing. And somehow they came out with a 3 based on pretty good educated guesses. Not just guessing, but educated guessing, meaning they were able to eliminate some choices and give themselves better than a 20% chance. Anyway, hold them up. Let me see them. Hold them up over the thing so I can see a little better. Okay. Ooh, okay. Mostly A's, a couple of B's, E's, and C's mixed in, but mostly A's. Let's take a look. If you were to draw a line of best fit through the data, that was terrible. But if you were to draw a line of best fit through the data, what I've told you to think about residual plots is this. You are to think of residual plots as literally me picking it up off of the flat area, whatever, turning it horizontally and putting it back down. And there's a reason why I did that on A. There's a reason why I did that on A. Because it is A. Let me erase some of those lines so you can see a little bit better. But literally, if you draw the line of best fit through the data, and then imagine that this whole thing is picked up, turned horizontally, and put back down, that's what the residual plot is actually doing. That is why that answer is A. Aha. Let's take a look at this. I don't want to do that one right now. We'll come back to that one. Ooh. Do I have time? Okay, here's the thing. I don't have time, but I want to read this one together with you all. So don't worry about answering this one. I'm going to read this one with you. I knew I was running out of time. Which of the following are true statements about R? A correlation of 0.3 means that 30% of the points are highly correlated. No, that is not what that means. That is not what R is. R measures the strength of the linear association. It doesn't tell you anything about the percent of points that are highly correlated. That means nothing. 2, the square of the correlation, R squared, measures the proportion of the Y variance that is predictable from a knowledge of X. I mean, remember what I told you. R squared has multiple ways of expressing that definition. R squared talks about the percent of the variation in Y that can be accounted for by the linear model on X. The square of the correlation measures the proportion of the Y variance that is predictable from a knowledge of X. I mean, that's a fancy way of saying it. But that could be true. But let's look at number 3. Perfect correlation is when the points lie exactly on a straight line, results in R equals 0. That's not what you said earlier. It's either 1 or -1. Clearly, that's not true. I think 2 is correct. I think that's a weird way of expressing R squared. Yeah, it is. The coefficient of determination, the ratio of the variance or the variation of the predicted values Y to the variance of the observed values Y. Alternatively, we can say that this is a partition of the Y variance and that R squared is a portion of the variance from the knowledge case. Anyway, I love this kind of stuff. It's amazing. Anyway, make sure you put those back under my desk. I'm going to try and keep those markers with them. Hopefully they won't go too far. And we will be able to hit some more multiple choice on Friday. I would definitely like to hit some more multiple choice on Friday. We'll see how it goes. Anyway, there's the bell. Woo!